Welcome to the Picture Language Seminar. It's a real pleasure to be here with Emily Riehl today. I want to remind you that next week we'll start half an hour earlier. The talk will be by John Pan. And Emily is going to give us an introduction to infinity category theory, of which she's a great expert and has several books on the subject, and will tell us about this intriguing thing which we hope connects to quantum logic and quantum information theory. Emily, why don't you share your screen?
Great. Thanks very much. How does that look? Okay.
Beautiful.
Great. Thank you for this invitation. It's always a pleasure to have an opportunity to speak to new audiences. Firstly, I've dropped a link to the slides in the chat if you want to peruse at your leisure, but we'll go through it here as well. So what I'm going to attempt to do today is give a broad overview of a kind of 10-year research program with a collaborator, Dominic Verity from Macquarie University in Sydney. We've just completed a book that presents a new approach to the foundations of infinity category theory. And for the experts, I'm using infinity category in the way it's used in Cambridge Mass, so as a synonym for infinity one categories, a nickname for infinity one categories. So this is of course a challenge to speak about because firstly, the subject matter itself is very abstract. I mean, there's this joke that category theory, ordinary one-dimensional category theory, is abstract nonsense, and this is the sort of weak infinite dimensional version of that. So it's challenging as well. And also the motivations for infinity category theory are extremely technical. So infinity categories are propping up in different areas of mathematics to sort of be mathematically precise, to give the fine print in theorems that are hard to state and hard to prove. So I've assembled a small illustration, a small sampling of some of the theorems in the literature in the past decade or so that reference infinity categories. And again, these are very technical. If this is not your area, I don't expect this to make a lot of sense. But what I want to point out is there's often a headline finding in the theorem. So there's an analogy between n jets and n excisive functors. That's a term that comes from Goodwillie calculus. And but when you read the fine print of the theorem, how it's actually made into a precise statement that's proven, as opposed to just a slogan. This involves, in this case, the Goodwillie tangent structure on some infinity category of differentiable infinity categories. So somehow a phenomenon that people in these areas have observed is that infinity categories come in making technical statements of theorems. So similarly, there's a duality, a Cazul sort of duality between something called factorization homology of n Cabordisms with coefficients in an n-disk algebra, that's En algebra, if that term's more familiar, and a dual relationship between that and factorization homology valued in the formal moduli functor. So these are, again, an instance to give a precise statement of this theorem. Even though infinity category doesn't appear in the words I just said, this equivalence is implemented as an equivalence of infinity categories. Okay, so if infinity categories are kind of in the water where you swim, you might sort of wonder what they're about and what they're for. And there's a metaphor that I really like from Barry Mazur that describe the role of ordinary categories in mathematics. So Barry says that a category frames a possible template for any mathematical theory. The theory should have nouns and verbs, in other words, objects and morphisms, and there should be an explicit notion of composition related to the morphisms. That theory should, in brief, be packaged by a category. Now, let me try and explain what this is about for ordinary categories first, and then I'll bring the infinity categories in. So maybe Felix Klein or Emmy Noether had this idea that if you're interested in studying groups, so these mathematical objects that encode symmetry, groups are productively studied in conjunction with the homomorphisms between them. So these transformations that relate one group to another. And sort of the modern point of view on abstract algebra really foregrounds the category whose objects are groups and whose morphisms are the homomorphisms between groups. So you can you can characterize certain groups, for instance, the free group on some number of generators, or for the free product of groups, or the cyclic groups. You can characterize them just in the language of objects and morphisms in the particular category of groups. That's sort of the insight of category theory. And then you can sort of understand by analogy the relationship between group theory and the theory of rings, or the theory of modules, or the theory of monoids, because all of these are categories in and of itself. Okay, so a lot of progress in 20th century, I mean, not by any means all progress in 20th century mathematics, but a lot of certain areas like algebraic topology, in particular algebraic geometry, really lean heavily into this categorical language, to the point of view that you can't say what a spectrum is, or you can't say what a scheme is without employing categories. But as the objects that mathematicians study get more sophisticated, sometimes this language of nouns and verbs isn't enough. So I like to say an infinity category frames a template for a theory, for mathematical theory, with nouns, verbs, adjectives, adverbs, pronouns, prepositions, conjunctions, interjections, and so on. So what I mean by this is, if you're interested in topological spaces, then the categorical point of view, the one categorical point of view would be that it's productive to study spaces together with continuous functions between spaces. I mean, that is unquestionably true. You can understand the projective plane as a quotient space, and that's to say that it's a quotient space requires this surjective homomorphism from the square, if you want. But for more sophisticated constructions, you might be interested in higher dimensional morphisms. So not just the kind of structure preserving morphisms, but some sort of higher dimensional morphisms in the context of spaces. These are homotopies. If we're talking about manifolds, and a Cabordism can be understood as some sort of morphism between manifolds, then you might be interested in diffeomorphisms between the Cabordisms, or then isotopies between those diffeomorphisms. And there are a lot of natural mathematical contexts where there are higher dimensional morphisms, and that's what an infinity category is about. So in an infinity category, we have objects and morphisms between them. This is just like an ordinary category, except we call them one morphisms now to indicate that there will be higher dimensional morphisms that I'll mention in a second. And then the first point of difference is when we move from a one category to an infinity category, at least in the way the term is colloquially used, we're both adding higher dimensions and weakening the categorical structure. So what I mean by that is in an ordinary category, we have a composition operation. If I have a morphism F and a morphism G, then there's a composite morphism G composed F. So in a infinity category, there will be many potential composites, always at least one, but in general, contractible space worth of choices of composites. And we understand a particular composite as being witnessed by an invertible two-dimensional morphism. So that the two-dimensional morphisms sort of detect that some composite is, or some arrow can be recognized as a composite of some other arrows. I'll give an illustration of this on the next slide. And then when we're talking about three composable morphisms, so say an F, a G, and an H, then there, in an infinity category, there will necessarily be an invertible two morphism that witnesses a particular composite arrow. Here I've called that G composed F. And then there'll be another invertible two morphism that witnesses a particular composite H composed G of H and G. And then another two-dimensional morphism that's, well, two other two-dimensional morphisms, one that witnesses a composition relation between F and H composed G, and another that witnesses a composition relation between H and G composed F. So one of them is displayed in this diagram. It's this thing I'm calling gamma, but you should imagine there's a fourth invertible two-dimensional morphism on the back of the tetrahedron. So the data of these invertible two-dimensional morphisms that witness the composition relations form the boundary of a three-dimensional shape, in this case, a tetrahedron, and there will be an invertible three-dimensional morphism in there that's witnessing a coherence condition or witnessing the overall associativity of this composition relation. And this doesn't stop at level 3, this continues all the way up. And of course, also the two-dimensional morphisms need to be composable, and the three-dimensional morphisms need to be composable, and the four-dimensional morphisms need to be composable, and invertible in a weak sense, and composition is associative in a weak sense. And so there's quite a lot of composition data that is required in an infinity category. Okay, so that's the vague idea. Let me give you a motivating example. There's a classical invariant of a topological space that's maybe most familiar if I called it the fundamental group. So this is if you have a space with imagine a surface of here I've pictured a 3-hole torus, but pick whatever space you prefer. And let's say I'd specified a base point in that space. So the fundamental group is a group whose elements are based homotopy or sort of paths, or sorry, loops in the space from the point to itself, but not the loops themselves, really, they're based homotopy classes of loops. So if you can deform one loop to another loop, they count as the same element of the group. That's one way to describe it. An equivalent way to describe that data in the case that your space is path connected is instead as the fundamental one groupoid whose this is an instance of a one category now, and its objects are the points in your space, and its morphisms are paths in the space, but still up to this homotopy relation. So if you can deform a path into another, they count as the same morphism. So that's a useful invariant of a topological space, but it only captures the low dimensional information of that space. So it can count how many sort of one-dimensional holes you have in the space, but it can't see higher holes. The fundamental group of the two-sphere, the sort of boundary of a ball, is trivial. It doesn't give you any information. That doesn't tell you about the hole that's inside a two-sphere. But the point is the sort of algebra of points and paths in a space is really much more naturally an infinity groupoid. So it's an example of an infinity category. So it's more complicated to say what an infinity groupoid is. There's a bit of a trade-off here. A group is a familiar notion we teach undergraduates. Infinity groupoids, not so much. But the infinity groupoid really captures what's going on in a topological space in a way that the construction of the fundamental group does not. So what is this infinity groupoid? So it has objects, which are the points in the space. So we have one fixed ambient space, this surface of genus 3 in the picture I've drawn, but any space will do. The one morphisms are paths between those points. You can think of those as continuous functions from the standard interval into your space if you want. And then two morphisms are homotopies between paths. So in the picture here, I've drawn some homotopies in orange between paths. Three morphisms are homotopies between homotopies. So in the middle of this picture, I've drawn, I mean, it's hard to draw a three-dimensional shape in a two-dimensional picture, but in the red, you can imagine that as being some sort of three-dimensional homotopy, which in this case is maybe degenerate because the picture looks like a surface, and it continuing all the way up. So what I want to notice is, what I want you to notice in this example is it has some of the features that I described in the notion of an infinity category on the previous slide. So one of the things we mentioned in an infinity category is that you can compose one morphisms, but not canonically uniquely, sort of only up to an invertible two morphism. And that composition is associative, but again, not on the nose, only up to some higher dimensional homotopy. So if I look in this picture here and I trace a composable pair of paths, there is a way to compose paths. I mean, you just do the one path and then do the other, but there's no canonical parameterization for that composite path, or I mean, maybe you think there is because you sort of spend half the time on the first path and half the time on the second path, but then that is not an associative composition relation. So the reason when I described the one-dimensional analog of this construction, the fundamental group, I said that the morphisms are homotopy classes of paths rather than paths themselves, was exactly to force this composition to be sort of strictly defined, strictly associative, strictly unital in the classical sense. But the natural structure is not to take homotopy classes of paths at all, just admit the paths as genuine one morphisms, but allow composition to be witnessed by these homotopies, these invertible morphisms in the level up. Okay. I meant to say at the outset that I'm happy to be interrupted with questions, so maybe I'll stop here and see if somebody will ask. So,
yes, I'd like to ask a question. This is a very good example. But in this example, whether this infinity groupoid capture the homotopic class of this topological space. I mean, different homotopic class would have a different infinity groupoid, and the same homotopic class would have same groupoid. Is that the case?
Yes, absolutely. So yes, so this is Grothendieck's homotopy hypothesis. So Alexander Grothendieck famously proposed that when for any precise definition of infinity groupoid, it must precisely capture the homotopy type of a space. So two spaces are equivalent up to homotopy if and only if their fundamental infinity groupoids are equivalent in the sense appropriate for infinity groupoids. So absolutely, that's a very, very important point. Yeah.
But is that a theorem or that just a wish?
Well, it depends on whether you've defined infinity groupoid yet or not. So one of the things that I'll discuss in a moment is this definition on the previous page. This is not a definition. This is a schematic. It's a sketch of what an infinity category should be, but I haven't, this is not a definition that a computer would recognize as a precise mathematical definition, because it's not. So the way these definitions are made precise, and I will return to this point because it's a centrally important one, is through explicit models of infinity category or infinity groupoid. So for an explicit model of infinity groupoids, this is a theorem. If you're proposing a new model, then it's a wish, and if you can't prove this theorem for your new model, then your model is no good.
Okay. Okay, thanks.
But it's many models of infinity groupoid for which this is a theorem. So.
Yeah, here you mentioned the infinity groupoid, and what's the difference if you have infinity category? You know, what is modified?
Great. So very good question. So groupoid is a word that suggests that all of the morphisms in all dimensions are invertible. So here we have points; those are just points. But the one morphisms are paths, and you can reverse a path. So that's the sense in which a path is invertible. Homotopy is a higher path, and you can reverse those equally. So that's the sense in which those are also invertible. So infinity category really means infinity one category. And what that one tells us is that in an infinity category, the one morphisms do not need to be invertible, are not in general invertible, but the higher morphisms still are. So an example of an infinity category that's not an infinity groupoid is the infinity category of chain complexes, if that's a familiar notion. So the objects are chain complexes. The morphisms are chain maps. This is the same as the ordinary kind of one category of chain complexes. And then the two morphisms are something called chain homotopies, which are these degree one maps. And then there are higher versions of those which define the 3 and 4 and 5 morphisms. So the difference is whether every single morphism is invertible, that makes you an infinity groupoid, or whether there's some dimension where there are non-invertible morphisms. I guess another example of an infinity category that's not an infinity groupoid that's maybe relevant to this audience is the infinity groupoid of n Cabordisms. So the objects are n-1, closed n-1 manifolds, put on whatever adjectives you want. The morphisms are Cabordisms between those closed n-1 manifolds. So with, the boundary decomposed into two pieces. So there's the incoming boundary and the outgoing boundary. And I'm not taking classes or anything like that. The morphisms are literally just the Cabordisms. That's part of the advantage of working in this weaker setting. Then the two morphisms are diffeomorphisms between Cabordisms, rel boundary, which are invertible. And then we can have isotopies between the diffeomorphisms, which are also invertible. So that's the kind of prototypical example of an infinity category.
Thank you.
Yeah, Emily, I might be jumping ahead. So infinity groupoids can be associated with the type theory. So we can have a computational model. So these infinite categories, would that be possible to relate them to type theory in some way?
Right, this is under development. So in another project joint with Mike Schulman, we've proposed just such a type theory for our infinity one categories. It's kind of like cubical type theory in that there's some modification of the context.
Okay.
So homotopy type theory is related to this new cubical type theory that has different contexts that allow you to discuss cube variables. And we do something similar to admit some simplex shapes in our context. I'm not going to talk about that today, though there's a related formal language for infinity categories that I hope to get to at the very end.
Thank you.
Great. Okay, so what have we done so far? So infinity categories come up in mathematics, and the precise definition is complicated. I haven't given it to you. But here's an example to keep in mind for why the definition is what it is. So in particular, it's absolutely essential for the most mathematically interesting examples that we allow this kind of weak composition in all dimensions, which is what makes it so hard to give a definition. There's a corresponding notion of strict, fully strict infinity category that's very easy to define, and there are basically no examples. Okay, so what I want to present now are some curiosities. So say you're depending again on what mathematical community you're in, you may or may not have been observing people use infinity categories in talks. And if this is you, there are some curious things about their usage in mathematics today. So a first curiosity, there's this beautiful lecture series at MSRI from a few years ago from the Derived Algebraic Geometry program. The introductory workshop is where experts are meant to give expository talks, essentially introducing kind of fundamental tools in their field. And Carlos Simpson, a pioneer of higher category theory, gave this beautiful 3-hour lecture course, Infinity Categories, Why They're Useful. If you're curious why they are useful, you could read the abstract, which I've reprinted here, which mentions some of the applications. But what's curious about his lectures is that he doesn't actually give a definition of an infinity category into about an hour and a half in, until the sort of the middle of the series. And this isn't at all meant as a criticism of Carlos. I mean, he's using that time well to give some beautiful examples and some motivation, but it's still a bit strange that if you're meant to introduce infinity categories, that you wouldn't even define them until halfway through. Okay. So another curiosity is if you watch those lectures, and I encourage you, they're very nice, you might notice that the definition that Carlos uses, which sort of is something he was involved in developing and with Andrei Hirschowitz in this paper, Descent for the N-Champ, is different from other definitions that appear in the literature. So there's a paper that I very much like by Bovada Di Brito and Michael Weiss that uses a different definition of infinity categories. Another paper of Blumberg, Gepner, Tabuada uses a different one, and still another definition appears in Higher Topos Theory at various points, which is this famous textbook on infinity categories. And this is related to something that we've already acknowledged. So the competing definitions are, they're referred to in the literature as models. I don't love that term because model theory is a thing, and this our usage of model is completely different than what it means in model theory. This isn't that at all, but regardless, we call them models. And what a model of infinity categories is it's a precise mathematical definition that Bourbaki would recognize as a definition of a mathematical object. So they go by various names. There are quasi-categories. That's a famous model. Complete Siegel spaces is a model. Siegel categories. one completial sets. Those are the 4 models that I'm referring to here. But that's a curious feature from an outset. All of these authors are proving theorems about infinity categories, but they're proving theorems using a different definition, using 4 different definitions. So that's a bit strange.
So Emily,
Yes,
just,
please.
when you say different, is that a precise statement in the sense you can pin down how they are different, or just you believe they are different?
They're definitely different.
In what sense they are different?
Well, I mean, maybe a better question is in what sense are they the same? So, they're different in the sense that the categories they live in are not equivalent. So that's a pretty strong meaning of different, I guess. But
let me ask something. Suppose we define the classified space of all of them.
Yeah, so let me explain the sense in which they're the same, because that's more interesting. So they're the same in the sense that the infinity 1 categories, and in fact, better, the infinity 2 categories in which they live are equivalent. So that's a weaker notion of equivalence, but sufficient for this context, or the kind that's kind of appropriate to this context. So, I mean, part of what's challenging in this area is that to develop the theory of infinity categories, you, to some extent, sort of need a meta theory of infinity categories to develop that theory in. And it makes it challenging to do things fully rigorously. I mean, there's a solution to that problem that I'm posing, but yeah, so they're different in the sense that, like, if you write a paper that explains how to convert from one definition to another paper, you can get that published in a journal because you've made a significant contribution.
Okay.
But they are equivalent in the sense that these different models of infinity categories each live in some categories, in fact, some infinity 2 categories, and those infinity 2 categories are equivalent as infinity 2 categories.
But that just means, in a sense that the truncation of them, at a certain point is the same, right?
Sure, yes, yeah. So if you have a particular infinity category that you care about, and Cabordisms say, you can instantiate it in any model.
Mm-hmm.
So
okay,
yeah. But I mean, it is maybe this is a natural transition. I mean, the problem, though, is that the theory of infinity categories has been developed to a large extent in the models. So André Riehl pioneered this task with the quasi-category model. He's the first one who really demonstrated that you can extend ordinary category theory to infinity categories. He was using quasi-categories, and he wrote, many unpublished manuscripts that are kind of widely circulated. I read some of these as a PhD student, for instance. But the problem is that his definitions of, fundamental categorical notions, which are things like, adjunction and limit and colimit and Cartesian fibration and con extension and so on, his definitions refer to the specific features of that model. The notion of an adjunction is a map to delta 1 so that is a Cartesian fibration and a co-Cartesian fibration and blah, and blah, and blah. And this involves some horn lifting property. And it's the horns and this one simplex that I mentioned there are particular features of the quasi-category model, and there aren't quite analogs of those objects in the other models. So it's not entirely straightforward to transfer a definition from one model to another model. And so therefore, there's this question: if you've proven a theorem in one model, can you use that theorem in another model? So a famous example of this, maybe most important theorem in category theory, is the Untitled lemma. And there was this paper that appeared that reproved the Untitled lemma, which had been proven in quasi-categories in a complete Siegel space model, in a different model. And that's, so the question is this necessary? It's quite distressing if it is, because the experts will know that developing the theory of infinity categories in just one model is very hard. Jacob Lurie is the famous source for a lot of these theorems, and he's written three books, higher topos theory, higher algebra, spectral algebraic geometry, that are thousands of pages in total. And if you had to redo that in all of the other models to be able to use these theorems in the models that more often come up in mathematical physics, for instance, that would be a bad state of affairs. And the experts certainly recognize that the models should somehow be beside the point. They're necessary, or they seem to be necessary to give precise statements and proofs of theorems. Yet, you know, the model is not the thing. And the notion of an infinity category should somehow supersede the models that make it into a precise definition. And indeed, when Jacob was first writing what became higher topos theory, there's this paper on infinity topoi, which you can read on the archive. He says at the start, you know, we begin in section 1 with an informal review of the theory of infinity categories. There are many approaches to the foundations of this subject, each having its own particular merits and demerits. Rather than single out any of those approaches to the foundations, he's referring to the models here. We shall attempt to explain the ideas involved and how to work with them. The hope is that this will render this paper readable to a wider audience, blah, 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 while experts will be able to fill in the details missing from our exposition in whatever framework they happen to prefer. So this was a little bit before my time, but my understanding of the history is that early readers sort of felt that there weren't enough experts, that it was too hard to translate this sort of model independent, this kind of schematic approach to infinity categories into a particular model. It was too hard to make things rigorous. And so when Jacob ultimately wrote higher topos theory, he did so using the quasi-categories model, using one of the models. But there's definitely this kind of ultimate aesthetic preference of everybody working in this field to work with infinity categories in a model independent fashion, to not have to spend so much time fussing over the particular details of each model, to not worry about which model you're using, to take a theorem proven in one model and an example constructed in another model and combine them together. And that's what our project is about. So what Dominic and I have developed is a new approach to the foundations of infinity category theory. We've presented it in a book, and it's intended as something that you could read first, if this could be a first introduction to infinity categories. And it is model independent from the start. So, so it does not require you to firstly develop the theory of infinity categories in one model and then transfer it to other models. We work in what I would describe as a synthetic fashion, where we are phrasing our results in a language that can apply to all of the models simultaneously, as opposed to the kind of traditional approach, which was to phrase definitions in a way that referred to specifics of a particular model. So how this works is we essentially apply the philosophy of category theory to the development of category theory. So rather than rather than focus so much on an individual infinity category in itself, what we do is we give an axiomatization of the category, the sort of much, much bigger category where infinity categories live as objects. So each model, quasi-categories is one model. The object is itself a category. The objects are the particular quasi-categories, the particular infinity categories in that model. But there's this larger thing we call an infinity cosmos, which is the full totality of all quasi-categories. And then there's also an infinity cosmos of complete Siegel spaces, and also an infinity cosmos of Siegel categories. So there are infinity cosmoi for all of the different models. And what we've observed is that you can give a short axiomatization of some of the features of these categories, these infinity cosmoi, and then prove theorems about their objects, prove facts about the infinity categories themselves from those axioms. So because we have this abstract axiomatization, we're proving theorems from those abstract axioms, then of course it specializes to all the examples. So this is the way in which we develop the theory of infinity categories in a model independent fashion. And then an advantage of this approach is that it also allows us to very explicitly address this question of change of model. So we can, a change of model functor will be a functor between infinity cosmoi. We call them cosmological functors. And we can characterize when those change of model functors are equivalences, in a sense appropriate to infinity category theory. So we call these bi-equivalences. And then prove that such change of model functors preserve, reflect, create features of the infinity categories in the particular models. So with this kind of abstract, axiomatic, synthetic, if you will, setup, it's kind of transparently obvious that, theorems about infinity categories, so I'll mention one in a few minutes, right adjoints preserve limits, that are proven in this abstract synthetic fashion transfer between models, because the original proof is kind of agnostic to what model you're in. So of course it applies to every model. But really, really, really crucially, we can also import theorems from the literature. So a generic theorem about infinity categories has probably been proven in a particular model using techniques that are special to that model and don't necessarily transfer between models. So we refer to these as analytic theorems. They're proven using the coordinates of the model to extend that metaphor. And we prove also that even though in that case you can't transfer the proof to another model because the proof might not apply mutatis mutandis, but nevertheless you can transfer the result, assuming that the statement can be expressed in this formal language. So not literally every property of infinity categories is invariant between models, because not literally every property of even ordinary categories is invariant under equivalence between categories. There's something subtle there. There's this notion of evil statements in category theory that are not invariant under equivalence. So we have to be careful when we introduce this formal language to describe model independent statements, but there is a formal language, and I'll tell you a tiny, tiny bit about it in a bit. So this is the main overview. I'll pause here for questions and then we can carry on.
Yes, I do have a question, Emily. So,
Please. Yeah.
When you answered my question earlier, so I can maybe, I don't know if it's correct, wrong deduction that the theory you have developed or you are developing is basically to embed all these infinity one categories into infinity two. And then you can try to see, how they will become the same when they consider inside this bigger infinity two category. So I can imagine in the future, if people try to develop, a equivalence of those infinity one category considered as a subset of, say, infinity three.
Mhm.
If you don't do carefully, might be inconsistent with your theory. If that's a possibility, that those infinity one categories contains more than just you can see from infinity two. They have some other things you just don't capture. What I'm thinking is your theory is like kind of the MacLane-Ellenberg axioms for homology theory, although that's for a functor.
Mhm.
If you only care about homology, that can be completely categorized. Just write down a bunch of axioms, and then no matter which theory you get, you will always get the same homology. But if you want to be really, really subtle, then you know that this is only true for some good topological spaces. You can cook up really bad topological spaces which don't fit into this. So that's my analogy of what you try to do, which is kind of develop a Ellenberg, MacLane axioms. You categorize infinity one categories. If only care about certain properties of infinity one categories, and then you can just categorize when you will get them by your axioms. If that's a reasonable thinking of your theory.
It's a reasonable concern, but I don't share it. So first thing to say is the natural category in general, in which infinity n categories live as objects is an infinity n+1 category. So you always bump up one dimension, but never more than one. And the reason is that, an infinity one category does have higher dimensional aspects, or an infinity two category, it does have 3 morphisms and 4 morphisms and so on, but they're all invertible. So there's only just the way that morphisms between infinite dimensional categories are defined. The layer of non-invertibility always extends one further, but never more than one further. So that's one approach to an answer. So infinity one category theory should be developed in an infinity two category, where infinity two category theory should be developed in an infinity three category. But I can't imagine what I would do with an extra dimension of non-invertible morphisms. I don't know how I would define them.
Okay. Okay.
But there's another answer as well, which let me state
Yeah.
is that I'm not gonna, I'm trying to keep the technical level of this talk down a bit, so I'm not gonna address this, but the real framework, I mean, I guess this is related to the formal language that'll appear on the very last slide. So the real framework where we develop the full formal category theory of infinity one categories is not merely an infinity two category. It's something called a virtual equipment. So it's an infinity two category that's paired with this other infinity two category of modules, where modules are also called profunctors or correspondences. And these are a vehicle to express universal properties involving infinity categories. And you're absolutely right in suspecting that just the infinity two category itself is somehow not enough for a fully robust theory of infinity one categories. We really do need this secondary setting involving the modules between infinity two categories.
I see. Okay. Okay. Thanks.
So
just one quick thing. I'm a little bit surprised you say you have to pair with an infinity two category, because I would guess you would pair infinity two with an infinity one, in the sense that you want to study the representation theory of infinity two, and normally you lose one level when you do. So I'm thinking you pairing. When you do pairings, that's like representation theory, right? Think about a product of vector space. So
I didn't mean pairing in a technical sense there.
Oh, okay.
So pairing is accompanying. So yeah.
Okay. Okay.
Yeah.
Okay. Thanks.
Yeah, I have a quick question. So
Sure.
there are synthetic spaces that Mike Schulman is talking about, spaces that are simultaneously topological and homotopical.
Mhm.
If you want to construct a higher order of these spaces, synthetic spaces, can this framework be used?
That's a great question. I don't know. So yeah, that's I mean, so what you're referring to is sometimes it's called cohesive homotopy type theory, which allows and this I think is a super cool idea and a really cool development, and it's also happening in parallel under the name condensed mathematics by Schulze and Clausen, and also Peter Hain and Clark Barwick, pyknotic spaces. So there's this idea that's emerging in different areas that the notion of topological space is trying to do too much work. And their spaces are used for too many different things within mathematics. There's, the classical, set equipped with a topology, but then spaces are also homotopy types or infinity groupoids really. And somehow those two directions need to be separated. The sort of the cohesiveness or the, are these points near each other? Are they far each other is kind of one role played by topological spaces, but also the kind of broader, how many holes are there in the shape? How many, whatever's, there's the homotopy type and then there's the topology direction. So there's some very new work being developed in different contexts, one of which is homotopy type theory, another which is kind of classical foundations. And I'm still learning about that myself, so let me not comment any further. But yeah, very exciting developments. I think the way we're going to think about topological spaces in 20 years will be totally different from the way we do right now.
Yeah, excuse me. I have a question about this relation to the N category.
Sure.
In the infinite N category, all the higher morphisms are invertible. They define equivalence class. Mm-hmm. What if you reduce those equivalent relations as identity? Did that reduce infinite N category into the N category?
Right. So there's a notion of infinity N category, and then there's a notion of N category. So what an N category is it has, objects, one morphisms, two morphisms up to level N, and then nothing above it. So only identities, if you will. So an infinity N has morphisms up to level N, and then invertible morphisms all the way up. So if you had an infinity, so I guess an N category can be regarded as a special case of an infinity N category, where there's just nothing above a certain level. Conversely, an infinity N category can be quotiented to make an N category by replacing the top level morphisms with equivalence classes, if you want.
Okay, I see.
Yeah.
Thank you.
Sure. Yeah, and one of the So there's a famous example of infinity n categories in the literature, which involves this Bayes-Dolan Cabordism hypothesis classifying TQFT, sort of n-dimensional TQFT. And the original statement was, or the original statement of the conjecture was for n categories. You know, it's saying that the Cabordisms between n categories should be classified by a dualizable object. But an insight of Jacob Lurie when sketching a proof of that Cabordism hypothesis is that actually when you extend the statement to infinity n categories, when you extend your category of Cabordisms to include these diffeomorphisms, not just diffeomorphism classes of manifolds, but actually diffeomorphisms as data, and then isotopies between those as higher data, and so on and so forth. When you extend it to infinity n, sort of fully extend the TQFT, then you can leverage these higher morphisms in the proof. And that was a crucial insight in his approach to proving that theorem. So it's a subtle difference between these notions, but I guess I'm of the point of view that I'm happy to work with a more complicated categorical structure at the cost of not taking equivalence classes anywhere, or for the benefit of not taking equivalence classes anywhere. Okay, let me, maybe I appreciate this discussion. Thanks for all the interruptions, and please continue. So what I'm going to try and do is sort of briefly give you a tour of what this looks like. So, I mean, that's what we've seen already is enough of a takeaway. This is what this project is about, but let me get a little bit more into the technical details to convey a small sense of the mathematics. And I'm sure I won't have time for everything, and that's totally fine. We'll do what we do, and then we'll stop when we're done. So so the theorems that we prove, so our manuscript is, you know, some 600-page book where we prove a bunch of theorems in infinity category theory. These are theorems that have analogs in ordinary category theory, and I thought I would just signal or highlight one in particular so we can discuss it. So, and let me try and come down to earth as far as possible. So I'm going to prove for you that distributivity of multiplication over addition for natural numbers. So in a particularly categorical way. I mean, of course, there are other ways to prove this. You can use induction or something, but let me prove it in a categorical way. So firstly, you could ask, what are natural numbers? What are cardinalities? I mean, they describe the sizes of finite sets. So if I want to prove an equation between natural numbers, I could categorify that equation, replace the numbers a, b, and c in orange with sets a, b, and c with those sizes. So A has A many elements, B has B many elements, and so on. And then if I reinterpret the symbol times as the Cartesian product and reinterpret the symbol plus as the disjoint union, then this set on the left, which is the Cartesian product of A with the disjoint union of B plus C, is a set whose cardinality is little a times B plus C. And the set on the right, which is the disjoint union of the Cartesian product of A with B and A with C, is a set whose cardinality is A times B plus A times C. And so if I construct a bijection between these sets, an isomorphism between these sets, then I will have proven that relationship between natural numbers. Okay, so by the innate lemma, if to construct an isomorphism between sets, it suffices to construct an isomorphism between functions, that construct a bijection, natural bijection between the set of functions from A times B plus C to X and the set of functions from A times B plus A times C to X. So if I had a bijection like this, then I could let X be either this left-hand set or this right-hand set and transfer the identity functions across, and that would construct for me an explicit isomorphism. And so now that I've, in a sense, maybe made the problem more abstract, I've replaced this equation between natural numbers as a natural bijection between sets of functions. I can give a very, very general proof. And this is a special case of a theorem that I'll discuss on the next slide, which left adjoints preserve colimits. So if I had a function whose domain is the Cartesian product of A with the disjoint union B plus C and whose codomain is X, then by currying, that's equally a function that takes as a single variable the disjoint union of B plus C and that outputs a function from A to X. But then by sort of case analysis, that data is equivalently the data of two functions one from B to the set of functions from A to the X, and one from C to the set of functions from A to X. And now I can uncurry both of those functions. And now I have a pair of functions, one from A times B to X and one from A times C to X. And then I can pair those together and get a single function out of the disjoint union of A times B plus A times C to X. Okay, so this is just, I guess, an illustration of a proof in the style of category theory of some very, very concrete fact. And the reason I like this proof, and sort of this last part in particular, where I take a function like this, I transpose it into a function like this, I then decompose it into a pair of functions like this, transpose again, and then pair those back together. So this is a very general argument. I'm transposing, applying the universal property of the disjoint union, which is an instance of something called a colimit, transpose, and then again apply that universal property. This is a general proof of a result in category theory called left adjoints preserve colimits. So left adjoint refers to a particular functor. It's a morphism between categories, so something that converts a set into a group or a set into a space. Left adjoints are like free constructions in general. And colimits are things like gluing spaces together or taking disjoint unions or direct sums. Those are all instances of colimit constructions. And the point of this discussion is this is a very general pattern in mathematics. This is kind of how category theory appears in mathematics. There are these very general patterns where you observe some linear isomorphism in vector spaces or some relation between free groups or something or other involving the tensor product. And there's a common reason for all of these observations that is expressed in the language of category theory, and in this case, in this theorem that left adjoints preserve colimits. And a nice thing about abstracting this relationship between constructions like the tensor product and the direct sum, thinking about it as a relationship between an adjoint and a colimit, as opposed to just between two constructions on vector spaces, is once this is phrased as a theorem in category theory, we get a dual theorem for free. So sort of famously, if you look at the axioms in projective plane geometry, you can swap points and lines and the axioms remain true. And so there's this principle of duality that any theorem in projective geometry has this dual theorem where we interpret the statement. So there's the same, something very similar happens in category theory. If you look at the definition of one category and you have an example of a one category and then you formally turn around all the arrows, you exchange the domains and codomains and then necessarily also the order of composition, then you still have a category. This is a construction of the opposite category. So there's some duality in the axioms, which means that whenever there's a theorem proven in category theory, there's at least one dual theorem. In this case, the dual of most interest is that right adjoints preserve limits. So we have some complementary relationship involving forgetful constructions or Hom functors and constructions like products or pullbacks and things like this. Okay.
Quickly, Emily, I have a question about limits. So you mentioned in topology, colimit corresponding to like a gluing, this kind of thing. What does limit correspond to?
Right, so the product topology is a limit, then pullback is another limit. There's something called inverse limit, which you might know, those are also limits.
Okay, thanks.
Sure, absolutely. Okay, so the proof that left adjoints preserve colimits, or also the proof of the dual theorem that right adjoints preserve limits, is the one that we gave, that we illustrated in here. So there's sort of 4 steps. You transpose, you apply the universal property, you transpose back, you apply the universal property again. I want to explain now how this proof would look more formally in formal category theory. So I'm going to introduce sort of picture language, if you will, for ordinary one category theory. What this language is it's explaining composition by pasting of natural transformations in a 2 category. So if I were to introduce this in a completely understandable way, I'd have to spend the entire hour on it, but let me just treat this as an illustration. So if A and B are ordinary categories, the definition of an adjunction that I referred to here, this is the thing like the free construction or the tensor product, involves a pair of categories A and B, a pair of functors, U and F. So traditionally F is like a free functor and U is some sort of underlying set construction. Maybe A is some category of algebras over the base category B. And then there's additional data of a natural transformation. This is one of these, this is the two-dimensional morphism between one categories. So one category is naturally sit in a two category. There's a two-dimensional morphism that we depict with a sort of double arrow to indicate that it's a higher dimensional arrow. And this is a two-dimensional morphism whose source is the composite FU, so the composite of the functors, and whose target is the identity functor on A, which I've depicted by drawing an equal sign. So this is a two-dimensional morphism. And to say that it forms part of the data of an adjunction, I need to specify a universal property, which is to say that this triangle is absolute right lifting. And what that means is that if I have another natural transformation, this alpha here, which you can read in line as on the left, so its domain is FB and its codomain is A, then it factors uniquely through epsilon in the way that's indicated by this pasting diagram, which I don't have a lot of time to explain, but there's some graphical calculus for natural transformation composition that is very visually useful. But in any case, what the factorization produces, the corresponding thing to this alpha, is another natural transformation beta from B to U of alpha. And this is the transposition relation of an adjunction. So there's a bijective correspondence between these natural transformations alpha and these natural transformations beta. So this formulation of adjunction as an absolute right lifting diagram is not the most standard one. It's not one that you would find in most category theory texts, so it's easy to translate to the standard one. It's certainly equivalent to it. And the reason I've taken that point of view is you can define limits similarly. This is also a non-standard definition of limit, but it's equivalent to the original one. So a limit is something, the input of a limit is a diagram that specifies, some family of objects and morphisms inside a category A, and then the data of a limit is an object in A, the limit object, which I'm identifying with a functor from 1 into A. So this is a functor whose domain is the terminal category. So it's picking out, its image picks out an object in A. And then the limit cone is a natural transformation from the constant D-shaped diagram at that object L down to D. So the data of the limit cone is this natural transformation lambda. And lambda has a universal property that says that it's a limit. And what it is it can also be expressed by an absolute right lifting diagram. What that amounts to in this case is the statement that arrows in A from some other object to the limit object L correspond bijectively to cones over the diagram D, whose summit is that object A. So these are natural transformations from a constant diagram into the original diagram. That's a cone over the diagram. These factor uniquely through the limit cone. That's the universal property that it's expressed by this absolute right lifting diagram in the two category of categories, functors, and natural transformations. So if you accept those encodings of adjunction and limit and colimit, then it's quite easy to show that right adjoints preserve limits. There's a graphical proof that essentially these absolute right lifting diagrams can be composed vertically and canceled from the bottom. And together with a bit of two naturality, which is what's converting the picture on the left to the picture on the right to the picture, the picture on the left to the picture in the center to the picture on the right. These are equations between two cells in a two category. It sort of follows immediately from this composition cancellation property that if I apply a right adjoint functor U to a limit cone, I get another limit cone. Okay, so if you've never seen a two category before, I imagine that didn't make any sense at all, but the point is there's a kind of relatively efficient packaging of this abstract categorical argument in the language of a two category of categories. And maybe the main takeaway, and this is really a surprise to the experts, maybe you're inclined to believe it, but the main takeaway is that this is actually the proof of the analogous result for infinity categories, even though the statement of the result is considerably more complicated. So there is a strict two-category of infinity categories, infinity functors, infinity natural transformations. Quite surprisingly, the definition of a junction and limit that I gave are the correct notions in the strict two category. That's really the hard part of this story. Is it's surprising that in this truncated two category, there's this difference between a two category and an infinity two category, and somehow this two category does capture the correct notion of a junction and limit. That's a technical theorem that needed to be proven. But once we accept that, this two categorical proof proves the analogous theorem for infinity categories. Anyway, I'm happy to discuss this further, but maybe this is a natural place to stop.
Well, it seems that you've only got halfway through your slides, so why don't you give us a little overview of the rest?
Sure. I mean, we had an interesting discussion, and I'm quite happy with that. But let me just I'll just take 5 more minutes and say a little bit more. So what's required next is to explain how on earth a proof in two categories gives a proof for infinity categories. And the first part of this is to introduce the models that I was alluding to previously. There are 4 models that are recognized as the better behaved for technical model category reasons that I could get into, but maybe I won't. These are the models that, when I say our theorem works in all models, these are the models that I'm referring to. And they are connected by various change of model functors, which have been developed by our colleagues and can be understood as equivalences. So our strategy to develop the category theory of infinity categories is to work synthetically. We're going to give definitions and proofs of theorems that work simultaneously in the 4 well-behaved models, as opposed to leveraging technical details of any particular model. Now, our sort of axiomatic language, this infinity cosmos, which describes common features of these models, is very sparse. So it's not as if you can prove every single theorem that you'd ever want to know about infinity categories from our axioms, but you can prove a lot of theorems, and those theorems are much easier to prove in this sort of sparse language. And as I'll discuss at the very end, we can, our theory is compatible somehow with this analytically developed theory, which allows you to leverage sort of the full information of any particular model. So the point of this slide was just to illustrate that you can give a definition of an infinity cosmos. So to a certain community, if you're familiar with the language of enriched category theory, if you're familiar with classic abstract homotopy theory, like a Quillen model category, then the definition of an infinity cosmos is something that's relatively short. There are kind of 3 axioms. It's a category that's enriched over quasi-categories. That's what makes it an infinity 2 category. These isofibrations have no homotopic theoretic meaning, but they allow us to model equivalence invariant limit constructions in a strict fashion. That's a standard idea in abstract homotopy theory. And then we ask for certain limits of diagrams of infinity categories, which we'll use to build things like the modules that are a vehicle for encoding universal properties. But relevantly to my claim that this proof in some 2 category actually is a proof of a theorem about infinity categories, there's a quotient of an infinity cosmos. So an infinity cosmos should be thought of as some sort of infinity 2 category. But as we've discussed, we can quotient and take homotopy classes at the very top level and get an actual ordinary strict even 2 category. And this is the 2 category of infinity categories and infinity functors and infinity natural transformations. And it's really, really surprising that this 2 category is good for anything. Yet we can prove that constructions and definitions like of adjunction and limit and colimit and so on in the 2 category are actually the correct notion from the point of view of the full infinity cosmos. And once we use that, we can define an adjunction between infinity categories in the standard two categorical fashion. So this is just a definition of adjunction that you would take off the shelf from any book on category theory. And then you can take off the shelf proofs of theorems about the calculus of adjunctions, because it's been well known for decades that you can prove these facts about adjunctions in any two category whatsoever. And so now we're just applying those very general proofs to the two category of infinity categories, infinity functors and infinity natural transformations. And the proof of right adjoints preserve limits is exactly the same idea. So we can talk about limits and colimits inside this two category, assuming we encode it in the correct way. I mean, there's something a little bit delicate about putting the definition in there in the right way, but once you've done so, the proof that I showed you that right adjoints preserve limits and left adjoints preserve colimits is in fact the proof that we have in chapter 2 of our manuscript. So when, for the aspects of infinity category theory that are developed synthetically, meaning working in any infinity cosmos, it's kind of transparent that those features are model independent, because we never discussed a particular of any model at the outset. And so a lot of the theory of infinity categories can be developed in this natively model independent fashion. But importantly, again, not every theorem about infinity categories can be proven from our axioms, because our axioms are too sparse somehow. There are way more examples of infinity cosmoi than the ones that I've alluded to. But nevertheless, there's a formal language, which I could also describe, but would be also a talk in and of itself. So it's a formal language like first order logic is a formal language. You can teach a computer to write sentences in this language. And there's a theorem that leans heavily on work of Michael Mackay on his first order logic with dependent sorts, that any formula or sentence about infinity categories that's written in this particular language of a virtual equipment, that's the kind of real structure, this infinity two category called an infinity cosmos, kind of paired with category of modules. Any formular sentence that's invariant, that's written in that language, is invariant under change of model. So that language is quite technical to describe, which is why I'm not even attempting to do so in this talk. But I'm hoping that my collaborator and I will one day develop a proof assistant that, or sort of formalize some of this work. So you can have a computer tool essentially to help you write these correct sentences in this language. That's one of the things we're hoping to work on this year. So here's a summary and I'll stop there. Thanks very much.
Well, thank you very much, Emily, for a beautiful overview of this interesting new theory you're working out. I'm sure that there are lots of discussion.
Okay, can I ask a quick question again? It follows you as a topologist. I'm quite shocked by your statements. I wonder you can say a few sentences.
Sure.
You're saying in 20 years, I need to have a re-education about how to think about topological spaces. So could you say a few words more? What do you mean by this new kind of thinking about topological spaces?
Right. I mean, this isn't my story to tell. I'm directly working in this area, but I have colleagues who are, and I've been attending talks. But it's not that there's anything wrong with spaces. It's that they're kind of trying to do too much work. So there are there are two different kinds of theorems that you would learn about in a point set topology course, sort of an advanced point set topology course, undergraduate, graduate. So there are certain theorems that really are about topological spaces as they're commonly defined. So like the Brouwer fixed point theorem that, any continuous endomorphism of a two-disk has a fixed point is definitely a theorem about topological spaces. And what I mean by that is that the two-disk is contractible. It's the same it's up to homotopy, it's the same as a point. And the Brouwer fixed point theorem doesn't make any sense if I'm saying any function from the point to the point has a fixed point, because of course, the interesting content of that is when I think about the topological two-disk or any space homeomorphic to it, that a continuous endo function of that has a point.
Okay.
So that's one sense in which topological spaces are used. But another sense in which topological spaces are used are as homotopy types. And, certainly, calculations of homotopy groups of things. Defining what a homotopy type is as a topological space is, kind of beside the point. I mean,
Okay.
you have to start with the set, but a homotopy type doesn't really have an underlying set, or if it does, it has a set of path components. It doesn't have a set of points, really. There are a lot of areas of mathematics, I think infinity categories among them, where part of the reason that the definition of infinity category is so hard, if I wanted to fully specify one of the models, is really an infinity category is a collection of objects together with a homotopy type of maps between them. But it's hard to say, it's not hard to say what a homotopy type is. We do have language for it, but it's somehow unnatural to say it's modeled by this particular topological space, but only up to homotopy equivalence. So they're more sophisticated. That's kind of a low level point of view of what this idea is that there's sort of the homotopy, the shape is sometimes what it's called, sort of the shape of a space, which is its homotopy type. And then there's its cohesion, which is its kind of topology. And, and those are somehow different dimensions. But so I think this is coming up also in kind of derived algebraic geometry, where I'm going to get out over my skis in just a second, but
Emily, okay, thank you. I have to say this is a great talk. First time I really get something thinking about. I just want to quickly tell why I asked the question. So
sure, please, yeah.
Well, Xiaogang is here too. So many of us doing quantum physics, sometime we are wondering about what is a quantum space. So I always want to think about, there should be some kind of a variation of a topological space to capture quantum phenomena. So that's why I'm so interested in a different way to look at topological spaces, because the quantum notion of closeness is very different from the classical notion of closeness. So that's why I'm so interested in a new notion. But thanks for a beautiful talk.
Yeah, great, thank you.
So may I ask a question?
Please.
So because the only model I know about an infinity category is the Cauchy categories, and I noticed that in your definition for infinity cosmos, it also has similarity with, let's say, Cauchy categories. Then I'm curious, because here you have we have various different definitions, different models for infinity categories, and why is, well, let's say, when our Cauchy categories not well behaved, and then for example, Siegel spaces, why is it better in some cases?
Right, so the question is why would, so if I had to pick a favorite model of infinity one categories, I would probably say quasi categories as well. So it's totally reasonable to ask, why would we ever need another model? So a couple different reasons. I mean, firstly, certain examples, kind of the more geometrical examples of infinity one categories often arise more naturally as complete Siegel spaces or Siegel categories than as quasi categories. So the models that are used for the Cabordism hypothesis, for instance, are the complete Siegel space models. I mean, that also concerns infinity n categories. So it also refers to the higher, there's an infinity n version of all of these models as well. But anyway, certain examples arise more naturally in a different model. And of course, then you could translate them to quasi categories and do some stuff there and then eventually translate it back. But it might be better to just avoid that translation step. I mean, that's what really motivated the paper of Kazdan and Varshavsky that I mentioned at the very beginning that's redeveloping some quasi-category theory in the complete Siegel space model. Another thing is, if you've ever tried to prove technical statements involving isomorphisms in a quasi-category, or I guess these are usually called equivalences in a quasi-category. So these are the one morphisms that are weakly invertible. It's just massively easier to prove those facts using marked simplicial sets instead of ordinary simplicial sets. And that's what this one complicial set model is. It's essentially a version of the quasi-category model that marks the invertible one simplices. So for technical reasons, it's nice to use different models, but I think kind of more to the point, it's just useful to know that you can define things like limit and colimit and adjunction and Cartesian fibration and so on in a way that does not refer specifically to the quasi-category module. That the notion of adjunction as just it's a pair of functors between infinity categories together with a unit and co-unit transformation satisfying the triangle equalities is just a much simpler conceptual definition somehow than the one that you'll find in higher topos theory.
Okay, thank you. And another question I want to ask is that, so I expect that the proof you use to prove the right adjoint proof, the right adjoint preserve, I think is left limits, I think.
Yes.
So I expect that here you use the definitions of those right adjoints and limits. You're actually using kind extensions, right?
I am not actually. So we reprove the theorem. We prove the theorem twice in the book. So that's a good idea. The second time we prove it, we redefine adjunctions and limits and colimits as pointwise Kahn extensions. But the reason it takes, so this is in chapter 9 versus chapter 2, where this right adjoints preserve limits appears. And the reason it takes so long is there's a distinction between a Kahn extension, which you can define just in any 2 category, and something called a pointwise Kahn extension. And the naive 2 categorical notion of Kahn extension is too weak if we just interpret it in the 2 category of infinity categories, infinity functors, infinity natural transformations. The pointwise notion of Kahn extension is the correct one. But to explain what a pointwise Kahn extension is, we need to develop this calculus of modules or profunctors, and it just requires a bit more sophistication. So the definition of adjunction, or the encoding of adjunctions and limits as absolute right lifting diagram somehow is stronger than the definition that you're imagining involving Kahn extension. This has something to do with the philosophy of generalized elements, the universal property. We could talk about this more offline. So this proof looks very similar to the one that you're imagining using Kahn extensions. But that one wouldn't be quite correct unless you stipulate that the Kahn extensions are pointwise Kahn extensions. Yeah.
Okay, thank you very much.
Sure.
Do you have some notion of a generalized quiver? Because like with categories, you can look at quivers, and then with 2 categories, actually, it's also some kind of generalized 2 complexes, right? So do you have something like this?
Right. So you have to remind me what a quiver is. That's a directed graph.
Yeah. So it's actually, because what is the one of the saying, if you have 1 category, then it's quite well defined. You can have like one, you can have a graph. Yeah, indeed. But then if you go to higher categories, sometimes you can say that the edges of a graph have different colors, and then some kind of play, right? It's not 1-to-1. I don't think that every category can be realized in this way, but still there is a very big class of categories which can be realized in a way there is some kind of complex behind. And actually your pictures did look like you say when you were looking at 2 categories. I know that I know what you're talking about. It's not like topology and so on. It's
sure.
But there are some combinatorial objects. So I'm asking if you have anything like this.
Sure. So there's so it's possible that I'm interpreting the use of quiver in a different sense, but let me answer it regardless. So there's a notion of what we would call a simplicial computad. And what it's meant to be is a free infinite dimensional category. So, so like a quiver or like a directed graph can be understood as a presentation of a free one category. A simplicial computad is a sort of infinite dimensional version of that. And we use this heavily to develop certain technical aspects of the theory. So part of a main theme is that some definitions that can be described in this quotiented setting of a two category of infinity categories, infinity functors, infinity natural transformations, are really homotopically correct from the point of view of the infinity two category. And so a technical version of that for adjunctions, for instance, is that any two categorical adjunction extends homotopically uniquely to something called the homotopy coherent adjunction. And to give a definition of that, we absolutely use one of these simplicial computads. So some of these free presentations of an infinite dimensional category. And it's a really, that's also a fun story. There's a graphical calculus for the free.
Yeah, and actually on this kind of meta level, you exactly understood what I mean, because of course those objects you can tweak properties and so on, but it's, you understood the idea completely well. But then what I would like to say is that when you start to work with those objects with kind of three categories and higher, you get to some kind of additional compatibility conditions which you don't see on the level of like two categories. And I think if in the world everything is somehow equivalent, right, it should be some difficulty in your case as well, because
Sure.
if one looks at some kind of very simple-minded objects, then you don't have a problem with this. But if you start to look at something non-trivial, in a way it's arrows, right? If like in your arrows start to go in several directions, it can happen. It's very much like in your pictures. So then there is like arrows, how you like complete your saying squares, but then and again in your squares also there was sometimes there is a unique way to complete the square, and it may happen that the same square comes from different sides and completed in two different ways, and you have to have everything compatible. So how do you deal with this?
Right. So everything is way more complicated when you're moving to kind of the higher dimensional versions of these categories. So from infinity 1 to infinity 2. So in a completely separate project, I'm working with some collaborators right now to prove that of pasting diagram. Sorry, I'm trying to prove with some other collaborators in kind of a separate project, we're trying to prove that this kind of pasting composition that I illustrated, where we have these two-dimensional morphisms that sit inside some embedded planar graph and are all kind of compatibly oriented. We're trying to prove that that has a homotopically well-defined composite in an infinity 2 category. And you know, that's a very basic result somehow. You know, for ordinary 2 categories without the infinities, this is classical, but for infinity 2 categories, it's not in the literature yet. And because it's a lot harder than you'd think. So I agree, this is complicated stuff.
I think a related question comes up with topological TQFT. You mentioned the connection with higher category theory, but in high dimensions, how does there are compatibility conditions that may not work out?
Yeah, I don't know. I mean, most of this, so, you know, this project has things to say on the higher dimensional versions of infinity categories, but the main results are optimized for infinity 1, and it was hard enough at that level. So, yeah. I mean, a higher category theory is still very much under development, I'd say.
Well,
May I ask a question? I have another question. We know that there's a Greenfield center which connect one category to two categories. I mean, the fusion category to braided fusion category, which use one category and 2 categories. I wonder whether there's similar concept, some Greenfield center which map infinity n category to infinity n plus 1 category.
Mm-hmm.
So
I don't know the details of that. Right, I don't know the details of that specific construction off the top of my head, but I imagine so. I don't know, I'd have to think about it. No.
I see.
May I ask a question?
Please.
I was recently reading your paper, two category theory of quasi-categories, and that two category theory does not have all limits, but certain weak limits, and also not all power objects. Does this category of infinity categories and model independent one, does it have all limits and colimits and all power objects, cat powers, I mean?
Great. So the two category that I was referring to in this talk, where is it? Is the same two category as the one in that paper. So when we wrote that paper, we hadn't yet developed the notion of infinity cosmos, but in the language that we would describe it now, that paper is referring to the infinity cosmos of quasi-categories. And then, sorry, I'm not on the right slide. And then the homotopy 2 category of that infinity cosmos is the 2 category we developed there. So the answer to your question is it only has weak 2-dimensional limits, so weak powers and weak comma objects and things like that, weak pullbacks. It does not have strict 2-dimensional limits. And we don't, in our axiomatization, assume that it has any colimits whatsoever. However, there has been a new development since that paper is written. So some of our colleagues, John Burke, Steve Lack, and Lucas Vokovic, have introduced a notion of accessible infinity cosmos. Accessible is used similarly as an accessible category. It's a similar notion of accessibility. And because our examples of infinity cosmoi ultimately derive from combinatorial model categories, literally every infinity cosmos that appears in the book that we've just written, and there are maybe, I don't know, 30, literally every one is an accessible infinity cosmos. And the upshot of that is that, so in an infinity cosmos, at the level of the infinity cosmos, we all have all of these strictly defined limit constructions that satisfy simplicity enriched universal properties. Because of accessibility, we have analogous colimit constructions that satisfy simplicity enriched universal properties, but only weakly. So up to equivalence as opposed to up to isomorphism. But what that means in practice is essentially you have all of the weak colimit constructions as well. But maybe in a very slightly weaker sense than the weak limit construction.
So it's weakly complete and co-complete.
That's right.
Okay.
That's right. And that's super cool because there's a whole bunch more that we'll be able to prove using those colimits, but future work.
Okay, thank you.
Sure.
Well, Emily, that was really beautiful. Thank you for connecting it to so many different interesting things. And I'm sure there'll be a great more of these connections. So we look forward to your coming back again and giving another talk. Thank you.
I appreciated all the questions and commentary. That was a lot of fun for me. So
well, we look to the future. Bye-bye. See you next week.
thank you.
Thank you.